Muy buenas tardes tengan todos ustedes, estimados clientes, amigos y equipo de Vector y Vector Global. Quiero darles las gracias por acompañarnos en esta videoconferencia, la cual forma parte de un variado ciclo temático que hemos preparado para todos ustedes y con las que buscamos mantenerlos actualizados sobre la manera en que nuestro entorno de negocios va evolucionando y se ajusta a los tiempos que hoy vivimos. Así como en nuestra videoconferencia del mes anterior tratamos el tema de la innovación y sus implicaciones en el mundo financiero con asuntos disruptivos como las fintech, en esta ocasión quisimos hablarles sobre el tema de la sustentabilidad social, que no es ajeno a ninguna industria y es por eso que hemos invitado al profesor Steven Chu, Premio Nobel de Física en 1997 y secretario de Energía de los Estados Unidos de América durante la administración del presidente Barack Obama. Él nos hablará sobre el calentamiento global y el futuro de la energía, un tema de gran impacto en el mundo financiero y empresarial, actual y futuro. El profesor Chu ha trabajado incansablemente por el desarrollo de las energías limpias, uno de los grandes retos para las industrias en las próximas décadas. En Vector y Vector Global estamos convencidos de que este tema, como otros tantos que hemos presentado y que seguiremos presentando en el futuro, son de vital importancia para el sector financiero mundial, más aún siendo Vector la única empresa financiera latinoamericana global con presencia en 19 ciudades de México y a través de nuestros brazos internacionales Vector Global y Vector Suisse con presencia en 11 países. Junto a nuestro invitado especial nos acompañarán Claudia Batle, directora de Asset Management de Vector Global, y Pablo Torruella, director de Asset Management de Vector, quienes nos hablarán sobre las estrategias de la empresa en el mundo de las inversiones socialmente responsables. Como les dije anteriormente, para nosotros es un placer contar con la presencia de nuestro invitado especial, el doctor Steven Chu, Premio Nobel de Física, secretario de Energía en la administración del presidente Barack Obama, profesor de la Universidad de Stanford, miembro de la Academia Nacional de Ciencias, expresidente del Consejo de la Asociación Estadounidense para el Avance de la Ciencia y actualmente jefe de la Junta Directiva de esta misma asociación. Entre sus aportaciones, ha publicado múltiples trabajos sobre física, biología y el desarrollo de las tecnologías limpias. En un momento cederé la palabra a nuestro invitado. Solo quiero recordarles que, como ha ocurrido en las conferencias anteriores, finalizada su exposición, tendremos una sesión de 20 minutos de preguntas y respuestas, para lo cual les pedimos escriban sus preguntas a través del botón del chat de la plataforma de Vimeo. En esta ocasión, de la misma manera que en la videoconferencia anterior, las preguntas le llegarán directamente a nuestros compañeros Claudia Batle y Pablo Torruella, quienes apoyarán al Dr. Chu para formularle las preguntas que ustedes envíen. Al igual que en otras ocasiones, les ofrecemos de antemano una disculpa si por cuestiones de tiempo no se puede responder a todas sus preguntas. Solo me queda agradecerles nuevamente por su presencia virtual y les cedo la palabra a nuestro invitado. Thank you, Mr. Chu, for joining us at this event. It is a pleasure to have you as our speaker. We are ready to listen to you.
Okay, thank you very much, and I apologize for the not so perfect sound, but let me just begin. I'm going to talk about two things in the next 40 minutes. One of them is change, where we're heading, and the other thing is the science and technology solutions to a sustainable world. So the first thing I want to remind you of is a temperature record. From 1850 to 2020, this is a graph of the average temperature worldwide. And as you can see, it has been climbing fairly steadily, especially since 1950, 1960. We're beginning to see things that were predicted decades ago. We're beginning to see increased droughts, heat waves, water shortages, forest fires, crop failures, and also rising seas. We also are seeing the underground water aquifers being depleted in many parts of the world. And if one shows a map of where there could be significant water stress in orange and especially in red, you see that The United States, Mexico, Australia, Southern Europe, all are going to, India and China will all be deeply water stressed. Now, let me just remind you of recent events, which have been very surprising to me. For example, 2020 ties a record for the warmest year on record. In 2019, temperatures rose to astounding 42.6 degrees centigrade in Paris in 2019, where they're estimated to be 1,500 deaths. 2020 heat wave, estimated 2,500 deaths. About 21% of Australia burned in 2020. There was record amounts of CO2 released in Siberia, 2.7 million acres of Brazilian rainforest. 2020 was the most active hurricane season on record. We are seeing excessive droughts over multiple years in both Mexico and southwestern United States. And this year, Canada and northwestern United States heat waves reached new records, double-digit records, including 49.6 degrees centigrade in Canada, where again, in the United States and Canada, estimated to be 1,500 deaths due to excessive heat only. Record flooding in Germany, US, China, and continued forest fires. So this is an example of this heat wave in July 2021, but let me just tell you where we're heading. Here you have a UN goal to keep the temperature rise below 1.5 degrees. That's going to require actually that the steady average carbon in the atmosphere is at below 400, really more like 350 parts per million. Well, today we're at about 415 parts per million. Here I plot the cumulative emissions worldwide. Cumulative is very important because once you put carbon dioxide into the atmosphere, half of it gets absorbed very rapidly by the oceans and by forests and other plants. That happens very quickly, but the other half cycles between the ocean and forest and land, remaining for thousands of years. And so that's why we say it's cumulative emissions that matter. That red line is the danger signal. If you cross that red line, you will have a 40% probability of going above 450 parts per million. And so this is what we're up against. And you see that most of the 3/4 of the greenhouse gas emissions occurred only in the last 65 years. Although this is a paraphrase of a great philosopher in Chinese Taoism. This is, if you don't change direction, you will end up where you're heading. And where we're heading is crossing that line. This is some recent data, and you can see the current time, and then these multiple colors start as projections as to what might happen depending on what the world does. If there are no climate policies, we will be predicted to reach 4.1 to 4.8 degrees centigrade. If we have our current policies, we'll reach 2.8 to 3.2 degrees centigrade. And so you see that the chance of staying below 2 degrees is rapidly slipping away. Now, you might not think that 4 degrees is much of a change in world average, but you also have to realize that the ice ages, which occurred 20, 30,000 years ago, the change in the temperature of the Earth was only about 5 degrees colder. And in that time period, all of Canada and the United States, the upper third of the United States, was covered year-round in ice. And so going to 3 to 4 degrees, the world will be profoundly different. All right, let me tell you some partially good news, and that's the science and technology solutions that some of them we have, others we will need to develop. The first good news is you probably all know that renewable energy costs have plummeted, And at the best sites around the world in solar energy, it's less than 2 cents a kilowatt hour, which includes the profit of the developer of these solar projects. These are sites in the Middle East. But the good news is prices will continue to drop, costs will decline, and within a decade and a half, one expects in many places around the world, the price of electricity due to solar power is going to be 1.5 cents a kilowatt hour. Just to give you an idea of what that means, these are production costs, including land use, maintenance, things like that. But today, wholesale electricity is being produced at roughly 5 cents a kilowatt hour. So solar and also wind are becoming very competitive with fossil fuel energy, coal, natural gas. All right. However, we also have to remind ourselves that the sun doesn't always shine, the wind doesn't always blow, and you need a backup generation capacity. Energy storage becomes crucial, and you also need a much smarter and enhanced transmission and distribution system. Let me talk about energy storage. And in energy storage, I'm going to show you a picture of my most favorite battery. Here it is. Where's the battery? Well, here you have an old-fashioned wind turbine in the Midwest of the United States. And when the wind blows, you pump water underground for irrigation, and it's pumped into this water tower. And so this concept of using wind energy or using solar energy when you have it and storing it in some other form has actually been with us for hundreds of years. And pumped storage, that is the idea of lifting water up from a low reservoir to a high reservoir, as in a hydroelectric dam, is the most effective storage of energy we have today, of electrical energy. And in fact, it's over 95% of all stored electrical energy in the world. The idea is very simple. You have an upper basin reservoir, a dam, and then over on the other side, you have a lower basin. And if you want to generate electricity, you just open a valve, you turn a generator, and you make electricity. These generators can be operated in reverse. And if you want to raise the energy, you can have incoming electricity, actually turning the generator now into a motor, and this turbine pump then becomes a pump and pumps the water back up a hill. It doesn't sound very efficient, but remarkably, if you have 50 meters of height between the upper reservoir and the lower reservoir, even as low as 40 meters, this energy storage can become 80% efficient round trip. That is actually more efficient than the utility scale flow batteries we are constantly thinking of trying to use. All right, now this is a very complicated graph. You don't have to look at that. Maybe you better look at the simple picture. And you say, how much energy storage do we need to get to a certain fraction renewable? I'll show the graph, but let me try to explain it. This is calculations, a techno-economical calculation done by former members of the Department of Energy when I was Secretary of Energy, 3 very smart people, and they said, let's consider the United States. It has very rich wind and solar energy. It's spread out over 4 time zones. Suppose we need 80% of our renewable energy coming from wind, solar, and hydro. How much energy storage, additional energy storage would we need? And it turns out to get 80% clean energy from those sources, you would need to store energy for approximately 100 hours. 100 hours doesn't sound like much. However, this is 100 hours of the average use of electricity in the United States, and 100 hours turns out to be 5,000, maybe even 10,000 gigawatt hours, but certainly 5,000 gigawatt hours to get to 80% renewable in one of the richest renewable energy countries in the world. How much battery storage do we have today? 2 to 3 gigawatt hours. So we're talking of 1,000 times more. And the other thing is that this energy storage, if you're using it once every 100 hours, roughly once every 4 days, you use that asset once every 4 days, and it has to be considerably less expensive. And so this is something else. And by considerably less expensive, this paper says, in the end, for that amount of storage, you need to drop utility scale storage, chemical battery storage, by tenfold, 10 times cheaper. All right, let's talk about some other good things. Now we're working on that, but it's not all there yet. But let's talk about things which will be coming to pass soon, and that's electric vehicles. But before I talk about electric vehicles, I want to remind you of a very fast transformation in technology that happened at the turn of the last century. And I show you pictures of New York City Easter morning, and it's a tradition in the United States. You dress up in your finest clothes and you have an Easter parade on Fifth Avenue. And in this Easter parade, you see people watching these people parade through, and you see very elegant horse-drawn carriages. Now, fast forward 13 years, same Fifth Avenue picture taken from a different vantage point, and you see something different. You see automobiles. In this 1900 picture, there was one automobile. In this 1913 picture, there was one horse-drawn carriage. So why did it happen so quickly? Well, it's surprising it happened so quickly because you had to have completely new infrastructure, a completely new oil, gasoline supply chain. You need better roads, you need repair shops. But the reason it happened so quickly was because of an environmental problem. And what was the environmental problem? Well, in New York City, there were about 160,000 horses by 1880, and they were producing 3 to 4 million pounds of horse manure a day. That's a lot of horse poop. And it was this pollution that you could smell it, you could see it, and all of a sudden, along comes what I call a poopless carriage, a horseless carriage, and people just went to this better, cleaner technology. Now, it was cleaner. However, it wasn't that clean. And here I show you a picture of Beijing on what we call a bad air day, when there's lots of industrial and vehicle pollution. And what we have found out in the last 20 years is that particulate matter, the very smallest particles, less than 2.5 microns in diameter, called PM2.5, is especially deadly. And very large studies, this is a more recent one, there are even more coming down, which followed over 300,000 people for nearly 13 years. This was not following people in China because the records are not so good, but following people in Great Britain. And what they found was that for every 5 micrograms per cubic meter of PM2.5, there's an 18% higher chance of getting lung cancer. Well, in Beijing in 2016, the PM2.5 count was 76 micrograms per cubic meter, not on a bad air day, average, year-round. And so if you only need 5 to get 18% higher chance of lung cancer, this was terrible. And people were beginning to cough, there was beginning to be asthma, older people were dying prematurely, and it was obvious the air was killing people, not only in China, but in India and many other places in the world. The World Health Organization guideline for clean air is 10 micrograms per cubic meter of PM2.5, but it turns out, of course, that if it's 10 micrograms, it's roughly 36% higher chance of getting lung cancer. So most people will not consider that clean air, but there's a huge resistance to lower that guideline because of the economic costs. At last, they're beginning to look at this. Anyway, it turns out lung cancer is not the most deadly killer for air pollution. Coronary disease, stroke, and are ahead of lung cancer, and there are a disease called chronic obstructive pulmonary disease, also fatal, also. And so it's these 4 diseases that are in rank order for people who smoke cigarettes. And it's the same because we're finding that identical or nearly identical carcinogens are on these air pollution particles as in cigarette smoke. So it's not a surprise. For that reason, we're hopeful that there'll be a very rapid switch to light-duty vehicles. These are personal cars, delivery trucks, pickup trucks. And this is one projection, the light blue internal combustion engines. And this graph tells you, it's making a guess that perhaps by 2040, the majority of cars sold annually in the world will be electric vehicles. That means that 55% of the new light-duty vehicles will still be combustion engines. These cars have a lifetime of at least 15 years. So this is 2040, and so by just doing the arithmetic, one realizes in 30 years or so, you've only replaced half the fleet, maybe less. And so it takes time. Of course, if it gets really desperate, you would have to start paying people to relieve them of their internal combustion engine cars and go to electric vehicles. The good news is that battery technology has grown remarkably fast and well. This is an example, This is an example of weight, energy density, watt hours per kilogram. That's energy per unit weight on the x-axis, energy per unit volume on the y-axis. And we're seeing that these are the old, where my pointer is, these are where the current technologies are for electric vehicle batteries. There's an expectation and a hope that it will soon go to 300, maybe 350 watt hours per kilogram. Now, these are beginning startup companies for the most part, hoping to get to this very high range in both volume density and in weight and in volume energy density. But we're pretty sure we're going to get to where my pointer is right here. And so that's very good news. The other good news is that people are developing very, very fast charging batteries. I'm on the board of directors of a company called Amprius, and we have extremely fast charging batteries where you can charge 80% of its full battery charge in about 20 minutes. And so if you could do that, now these batteries don't last that long. They're very good for drones and other things where you would be having them only last for 100, 200 cycles. But for automobiles, you want them to last 15 years, which then translates in normal use to roughly 1,000 80% discharge cycles. All right. So when will we get there with these fast charge batteries? I'm not sure. Maybe 5 years, maybe 10 years, something in that time scale. Imagine 350-mile range battery charges 80% in 20 minutes. That means you can charge 100, 200 miles in less than 10 minutes, maybe 6 or 7 minutes. Once you have that, that means on a highway, you can go into a rest stop. You can charge in 5 or 6 minutes to go another 150, 200 miles, and off you go. And so you can stop in a rest stop, you can go to the bathroom, and while you're discharging, the battery's charging. And so this would be very exciting. The fact that the energy cost of batteries is going to be much less than the energy costs of petroleum, diesel fuel, gasoline, will make this a no-brainer if the cost of an electric vehicle is comparable to the cost of an internal combustion engine car. The costs are coming down dramatically as well, and perhaps in 10 years, they will be comparable. Now, there are certainly materials issues, and there are two types of materials. On the anode side, there's lithium. And if 80% of the new cars by 2040 or 60%, whatever, are lithium-ion battery cars, then lithium becomes very expensive. And so we just published a paper last year in a journal where the senior postdoc on that project, Chong Liu, who's now an assistant professor at the University of Chicago, developed a mechanism for taking lithium out of salty water, including seawater. Seawater is especially important because the ratio of sodium to lithium ions is 20,000 to 1 more sodium ions than lithium ions. And yet, after one cycle of processing, you can change that ratio to 50-50. If you look at very salty water that comes from conventional oil drilling, that ratio is actually quite a bit higher, roughly on average 1 to 2,000. If you drill deeply, you find salt water everywhere. And what she found was that after one cycle, you're getting something like 93% lithium. Once you have 93, even 50-50, you can use chemical means to precipitate out lithium, and then you leave the sodium behind. And so she's working to further improve this. I and another postdoc of mine are working on new ideas, perhaps to get it even better. If either of these ideas work, this would be very good because this form of extracting lithium is very non-polluting. Unlike lithium mining or lithium extraction from very salty lakes, which you then evaporate, those are very environmentally polluting. This would not be environmentally polluting. So we're hopeful that ideas like these can actually come to play. Another thing that I'm working on, and many other people are working on, is on the cathode side. On the cathode side, there's a mixture of nickel, manganese, and cobalt, where cobalt is extremely expensive, even today. And again, if you say that instead of 3% car sales, you go to 80% car sales, cobalt would be prohibitively expensive because there will be run on the supply of cobalt. And so what we're trying to do is develop a lithium metal sulfur battery because sulfur is very plentiful. In fact, in order to use liquid hydrocarbon fuels and refine it from crude oil, most of the crude oil is high in sulfur content. And by regulation, air pollution regulations, you have to extract the sulfur to make low sulfur gasoline, diesel, and jet fuel. The oil companies are awash in sulfur. They have mountains of sulfur. They don't know what to do with it. And so if you can make sulfur batteries, there will be no problem in materials costs. In fact, a lot of what they do with it is they put it in tar to make blacktop and asphalt. And the asphalt is 30-40% sulfur. It's filler. All right, let me talk about something else very important. And it's a new agricultural revolution. And first, let me set the stage for why this is important. If you look at where greenhouse gases are generated, you have in the pointer the lower orange color, that's carbon dioxide emissions from fossil fuel combustion in industrial processes. Industrial processes mean industrial heat that we use to make chemicals, plastics, steel, cement, and so on. Then you have forestry and land use. This is this orange thing. Then you have methane, of which half of the methane is due to agriculture and animal raising for food. Then you have N2O. Virtually all of this is due to overuse of fertilizer that the plants don't use, and this creates N2O emissions. And finally, you have fluorinated gases that are used in refrigerants. So this is the main contributions of greenhouse gases. And what can we do to eliminate that? Well, first, let me remind you that agriculture has changed over the last several thousand years. I'm going to show you pictures of corn, and I will ask you to pick out what was the native corn 1,000 years ago and what is the modern corn today. And you'll see that the native corn, the naturally occurring corn, looks nothing like the corn we eat today because we've bred the corn and the corn plant to be so much more productive. We've also done that with animals. We have beef that we eat, pigs we eat, broiler chickens, and so on. This full circle is the natural lifetime of an animal, and the little red segment are the times in which after birth the animal is slaughtered. So for beef cattle, it's only 18 to 24 months, 1.5 to 2 years. Pigs, it's only 22 to 26 weeks. before slaughter. Broiler chickens, 40 days. So an American pig, by the time it's slaughtered in only 24 weeks, the average weight is 280 pounds. These are unbelievably bred animals that grow very, very fast in a very short amount of time. But they're also a bit artificial in many respects. These are domestic turkeys, the kind Americans eat during a vacation called Thanksgiving. You can find them in local supermarket. They may weigh 12, 14 pounds without the head and the insides and the feet. But these are only 3.5 months after birth. But they're so breast heavy because Americans like white meat that many of them cannot mate naturally and they're artificially inseminated. All right? So this is something that, again, is part of industrial breeding. Now, let's go to cows. Cows eat a lot of food. They grow up, but after 1.5 years, you have a very big beef cattle. But when they do that, they are also ingesting food. They're expelling gas, burping it out. It comes out the front end, it comes out the back end, and so on and so forth. And if you look at the annual CO2 emissions of the world, in the lower one is EU 28. This was made when Great Britain was still part of the European Union. The biggest emitters are the United States in this turquoise color, and China. China is now emitting twice as much greenhouse gases as the US, and the US emits more than the entire EU 28. But if you look at beef cattle and dairy cows, and if they were a country, they would be emitting at 2020, 2019, 4.6 billion tons of CO2 equivalent per year. And you see that's actually significantly more than the entire EU 28 plus Great Britain. Or the EU 28 was Great Britain. I guess it's EU 27 now. Let me say it again. If beef and dairy cattle were a country, the equivalent greenhouse gas emissions from just raising those animals and using them for milk, cheese, beef, is more than the European Union, comparable to the United States. All right. The other thing I should point out is if you look at all the biomass in the world, so you put on one side of the scale humans and the animals we eat, on the other side of the scale the rest of the mammals of the world, including all the mammals, you know, the squirrels, the chipmunks, the rats, the mice, the deer, the bison, you name it, all on the other side of the world, we would be 96% of all the mammal mass in the world. We profoundly geoengineered the planet. I should say also that where science is driving towards meat substitutes, that is meat tasting material based on plant food. This is much easier on the environment, and they're using exotic genetic modifications. For example, the bloody taste that one likes in ground beef is actually coming from a hemoglobin-like molecule, which they can get yeast to grow, and they put it in this plant-based material. Another agricultural revolution coming down the road is in raising plants in a much more efficient way. And here I show you a picture from Pivot Bio of corn. And here in the corn, you see the roots. And if you blow up the roots of the corn and magnify that, right at the border where the roots are with the soil, there's a region called the rhizozyme. And the plants can develop a symbiotic relationship between the microbes in the soil and the roots. This is done naturally in plants like legumes, like soy, but not done in corn. And so the idea is if you can develop a new set of microbes that would like to talk to a corn plant, and when the plant says, I'm hungry, feed me, the microbes give them nitrogen-based fertilizer. The nitrogen is obtained from gas in the materials in the soil, but not from fertilizer, from natural absorption of the atmosphere. And the plants are fed. The plants give these microbes nutrients to keep them near the rhizomes so that they're entering what we call a symbiotic relationship. And so this company has developed a set of microbes, but they weren't that productive. So they partnered with another company called Zymergen. And Zymergen is using a lot of genes, manipulating all the genes of these microbes. They use robotics for repeatability. They use machine learning to analyze what they should do in the next step. And here I show you, they're starting with an ancient microbial strain used in industrial production. And over the dark blue are the progress, the company who is making this stuff in industrial scale was steadily improving it. And by using modern machine learning, robotics, and big data, we can make much better progress. And so Zymergen is teamed up with Pivot Bio to not only improve corn, so the corn not only grows better using half the fertilizer, with the goal going to maybe only 10% of fertilizer, maybe a few essential ingredients. It's not only nitrogen, you need to replace it with other things as well. And so one is working on that. So this is an example on the right-hand side of Pivot Bio corn versus natural corn. And the corn is much happier, the productivity has increased. And so Pivot Bio is now beginning to work on wheat, and we would want to do this for all the major grains: corn, wheat, oats, rice. And if you can do that, you can really reduce much of that N2O emission, and fertilizer production is 2% of all energy greenhouse gas emissions by itself, just the energy cost of fertilizer. Now, let me come to the very end. I'm going to end a little bit early because we started a little late. And I'm going to tell you about something, if you want a sustainable environment, that you have to remember. And so I direct you to this website. This in the middle is Hans Rosling with his two children. He passed away recently, but his children have continued. And they have, it's called Gapminder, and it's a way of presenting much data of the world in a graphical form that the user can manipulate what they want in graph form. And so what he wanted to do was make available high quality data to people so they can massage it, understand it, and ask themselves different questions. So he called this website Gapminder, and I can use Gapminder and I can plot along the x-axis the average GDP income per person in each country. I choose on the y-axis the number of babies per woman on average over the entire population of the country. And here you see the year 1912. And it starts in 1800. When you see a straight line, that means there's no data. And then they start actually taking data. And so you have data for Germany, you have data for India, you have data for Mexico and the United States. Let's further go on. Mexico, green is the United States. Mexico is blue, India is red, Germany is yellow. And so now we've just fast forward to 2018. And what you have on the y-axis is the fertility rate. It turns out to have a steady population, you need on average 2.1 babies per woman. You think, why 2.1? Why not 2? Well, but there is childhood mortality and things like that. And so what is very surprising is that as the income increases, the fertility rate plunges. And in many countries like the United States, Germany, the fertility rate is less than 2. Fertility rate in the United States would be 1.4, 1.3 if it weren't for immigrants. In Japan, it is 1.3. They don't have very many immigrants. Many countries in Northern Europe also hovering around 1.4, 1.5. What's surprising, though, is that India is still a poor country, and India ends right here. In 2018, the average income in India is only about $6,000 per person, relative to the average income in the United States, $50,000 per person. 10 times poor. Fertility rates 2.3. So you don't even have to be that rich. The takeaway message is, in today's world, even before a country becomes super rich, fertility rate plunges. And is that good news or bad news? Well, economists say that's bad news because you want more children. Because if you have more children than older people, then you can use those children to support an older population. If you have equal fertility rate, steady state, if you have negative fertility rate, you have fewer young people to do the work to support the older people. And so they say, no, we don't want that. We want to actually have what's called rising population. In the United States, this is called a Ponzi scheme. We need to develop economies and develop ways of using technology so that you can have rising level standard of living with a declining population. It's possible to do that. It's really very possible to do that, but we have to change our mindset. And so to that, we also have to change a definition of wealth. Okay, the world needs a new model. How we define wealth today, it's GDP per capita. And what is GDP? That makes you use energy, resources, whatever, to make stuff, and you consume the stuff. If you want to raise the GDP of a country, you would want every family to have a car. When the country gets rich, maybe you want every family to have 2 cars. Maybe you want every family to have a house or an apartment. Of course, you want every family to have 2 homes. And so this is the production of consumption of stuff. We have other attempts at measuring wealth. For example, you can have GDP per person. It's a logarithm because when you get 10 times richer, your standard of living doesn't really increase that much once you get above middle class and poverty level. Certainly when you're a poor family or in developing countries, it really matters. But in addition to that, longevity, how long you live on average, and what's the level of education. These are measures of other forms of wealth, but also other forms of wealth could imply, the quality of your life in your old age. Do you feel safe and secure personally, your family? Can you have the means for satisfying your curiosity, not beyond your high school days, your college days, and continuing education, old age, and living comfort? These, I would think, are measures of wealth. And so we need a redefinition of wealth. I think technology and robotics and all these things can give it to us. And so let me close by reminding you of one of my favorite pictures. It's called Earthrise, and it was taken by Apollo 8. It was the first mission that orbited the moon in preparation for the moon landing. It was taken on Christmas Eve, 1968. I was a college student, and in this picture, you have a beautiful Earth silhouetted against the background of a landscape of a very bleak moon. And the astronaut who took this picture said, "We came all this way to explore the moon. And the most important thing is we've discovered the Earth." In this picture, we discover Earth as a beautiful place to live. The moon is not a good place to live. No water, no air, no magnetic field to shield you from lethal doses of radiation from the sun, ion radiation. And from this vantage point, Earth looks beautiful. Notice something else: black everywhere. We have nowhere else to go. Since 1968, we discovered we're altering the destiny of our planet. And if we don't watch out, we'll end up where we're heading. It's not a good place. We need the political will, the investments, better science and technology to make this change. And so with that, I thank you.
Thank you very much, Dr. Chu, for your very valuable insights on such critical issues. Now we're open for questions, which you can post in the Q&A section on your screens. So we have the first question, which is, what is your opinion, having said all that you shared with us? Do you think we still have time to reverse climate change damage?
Yes, we do. The reason I think we do is not because we're going to stay below 450 or 500, even 550 parts per million. We are developing technologies to capture carbon out of the atmosphere. And if we capture it out of the atmosphere and return it, sequester for very long periods of time, we'll reverse that. Now, let me also remind you that agriculture, the food we grow to feed ourselves, and the grasses we grow to feed our animals, that fixes carbon dioxide from the air and turns it into plant mass. And that fixation actually grabs from the atmosphere as much carbon emission as humans put out. But all of it circles around. And so if we can take that biomass, turn it into useful products, and put the extra carbon dioxide underground, or turn it into something which is mineralized, so it doesn't actually go back in the atmosphere, you have made a huge dent. And so, sorry about the phone. In any case, that's something we must do, we have to do. We start by capturing carbon dioxide from the surface, the point sources as well. But we're going to need to do that.
Thank you, Dr. Xu. Another question is, thinking in all the capital investment on the space exploration and not enough in clean energy, it is possible that humanity can colonize another planet before suffering catastrophic consequences of climate change?
No. I don't think we should think about trashing this planet and going to a new world. It's not like Europeans going to the new world and settling where there's air to breathe, there are things to grow. If you consider Mars, there's no atmosphere on Mars. There may be water underneath Mars, but not on the surface. There's no magnetic field on Mars. And so again, the solar radiation, the ions from the sun will actually be overwhelming. Even the journey to Mars, the radiation could be lethal. What about other planets? Maybe there's another planet somewhere. And if you think about that, if this mystery of going, now the nearest stars are several light years away. The way we can get out of the Earth's gravitational and the solar system's gravitational field is we approach a planet that's moving this way, and as the planet is moving this way, it whips along and goes out. So you can accelerate and get out of it. We can't use chemical energy rockets to do that. So then you can go a certain speed, but then you realize it's going to be hundreds of light years, tens of light years, tens of thousands of years away just to go 10 light years, because we're not going to be traveling the speed of light. We know how fast we can get by looking at the speeds of Voyager. Then you get to that planet, and you can't synchronize your landing with other planets. So you hit with a hard landing. It's just not it's a romantic image, but it's not. It's an irresponsible image because we really have nowhere else to go, not for the foreseeable future. This is our home.
Thank you. So we have another question. How should society demand more from companies and governments that take greater responsibility in this climate change problem?
I think the way you do it in a democracy is you tell your politicians, this is very serious. I care about my children. I care about my grandchildren. And I care about political instability in the world. You cannot rely on all the natural good graces and tendencies. There would be many businesses, I would think, that this is the way they make money. If you go and change, then they say, we'll go out of business. And I'm not going to do that. And so what people do, it's a very natural human tendency to say, well, maybe this is not really real. Or maybe there'll be a miracle that will save us all. And well, I'll just go doing my business until it happens. We cannot wait for a miracle. We have to help ourselves. And I think you tell your government leaders that this is what you want. You try to do it by personal choice as much as possible. And you buy things from companies who seem to really care about this, and personal choices in many other respects. We've seen what personal choice can do in the clothing industry. So you stop child and slave labor in South Asia. It really did make a difference. And so personal choice does matter because it gets companies to wake up. But we also need the politicians, and we need the scientists and engineers.
Another question, Dr. Xu, do you consider that the new generation are more environmentally conscious than baby boomer, for example?
Absolutely. I consider the teenagers and 20-year-olds, the people in college today, they care a lot more. There was a generation, my generation, I was at the beginning of the baby boomers. I think we cared a lot about things. Then there was a bunch of generations that were focused very much on making lots of money. But I'm beginning to see this turn around. And young people are saying, well, I'm going to eat less meat, or maybe I'll become vegetarian or vegan because it's good for the planet. They say, maybe I don't want a big house, or maybe I don't even want to own a car. I can rent these so-called zip cars and do that. And maybe I'll live in a city. Yes, it's a smaller place. It doesn't have a big yard, but it's ecologically much better, and I don't have to waste 2 or 3 hours of my life commuting. And so I'm beginning to see very sensible decisions by young people.
Thank you. We have another question. Do you consider hydrogen-based energy to be a good substitute for current ones? When do you foresee that it could begin to be used in a massive way?
It's not known. I think hydrogen will play a role in the future energy economy. It's a means of energy storage. The way one wants to use it is take very, very clean carbon-free energy, wind, solar, nuclear is carbon-free, turn that, for example, using electrolysis into hydrogen and oxygen. And so that is an economical issue. Can you make hydrolysis cheap enough? Maybe people are beginning to look at better ways of doing electrolysis of water, splitting water into hydrogen and oxygen. Right now we get our hydrogen from methane, natural gas. And what you do is you make hydrogen and you make CO2, and they vent the CO2. So hydrogen cars that drive on hydrogen, if they don't capture and sequester the CO2, it's actually no cleaner than fossil fuel. It is a little cleaner. You don't make as many particulate matters, for sure. But so for air pollution, it's better. But for CO2 pollution, no, it's actually no better. And so you have to make it in a clean way. I'm fairly optimistic that we will have some way of doing, but again, it depends. Also, you need a hydrogen infrastructure, hydrogen pipelines. The existing gas pipelines will become brittle. You can't use them. So new pipeline systems. And so you need a number of things. But I'm hoping that hydrogen will be part of the energy storage problem.
Excellent. Another question. It is a reality that the world belongs to everyone, but many times the economic condition of each country make a big gap. How soon will this technology reach Latin America countries, and how affordable would it be for these economies?
Well, again, first I want to say one thing, that the richer countries, the ones who developed 50, 100 years ago, have done the lion's share of the pollution, they're richer. And so I think they have a responsibility to help the poorer countries go faster and make the transition. And by go faster and make the transition, I mean a good thing. I don't mean, no, you stay poor, let us stay rich. Everybody deserves an equal standard of living, but it is possible to actually bootstrap beyond the normal development path that occurred in the industrialized, developed world 100 and 200 years ago. An example everybody can understand very easily is telephones. Telephones were invented in the United States. Alexander Graham Bell, he wanted universal telephone coverage in the United States, so he started a big program supported by the government, put wires, telephone wires, to as many homes as possible, because the great value of telephones is when everybody's connected. And now Bell Laboratories invented cell phone technology. Well, we don't need wires anymore. And so all of a sudden, developing countries don't need wires. Now, what can you do about that in developing countries? Well, I think solar energy is becoming so inexpensive, so reliable, that you can imagine in poor communities, especially in rural areas you don't have electrical power lines, but even if you do, solar power can be there. And especially in developing countries, you can use that electricity to pump water, for water purification, for irrigation. You can use that electricity to charge your cell phone. Most LED lanterns have a little battery, so you can use that to be lit at night instead of using kerosene lamps. You don't need to generate electricity from diesel fuel except when the sun stops shining, so it's emergency backup. So I see leapfrogging. Now, as energy storage gets better, it becomes even possible. But remember my picture of that water tower. You know, irrigation and purifying water are big deals. And finally, a refrigerator, a good refrigerator with maybe a quarter of it being ice and water. If it's well insulated, it can maybe go a day or two without spoiling your food. For most people, storing food for several days is life-changing. Unlike America, where we go to these big stores called Costco and you buy food for 2 weeks and put it all in the freezer, most people don't do that. In fact, it's much better to buy food every day. and so again, refrigeration for 1 or 2 days changes lives in a dramatic way. So these are things I think, again, can help leapfrog past the developed world.
Thank you. Now this is a tough question. What would happen if we cross that red line and reach the 2+ degrees?
Well, we're going to have to get the carbon dioxide out of the air. As I said before, let's pretend we go to 550 parts per million, which will be likely we're going to go to 2.5, maybe even 3 degrees. If we keep that, it's going to be very dangerous, but it takes time for that amount of carbon dioxide to warm up the globe. And the reason is very simple. The oceans are very cold. Once you go maybe 5 or 10 meters below the surface, you notice it gets very cold, even 3 meters. But by the time you're a kilometer in the ocean, it's very close to freezing. And the ocean currents that mix the top water with the bottoms of the ocean are very slow thermal mixing. So think of the bottoms of the ocean as like gigantic ice cubes. Now, you've just put greenhouse gases in the atmosphere. The sun's coming in. Suppose the energy coming in remains constant. The energy going out is not, it's less. So the temperature increases. The temperature increases until the emission into space increases, but also you've got to warm up the ocean. And for that reason, there's a time delay, depending on how much we've polluted. There could be 20 years, it could be 50 years, it could be 100 years. We don't know. But it's a long way. So it's like smoking cigarettes for the first 20 years, from 20 to 40, you stop, and then at age 70 or 80, you get lung cancer because the mutation started 20 years ago and 30 years ago. So this is what we're looking at today. okay? Because the ocean have this thermal mass and takes a long time to get really bad, we got to get rid of the carbon dioxide. It's also going to take time for Antarctica and Greenland to melt. Hundreds of years. It won't melt in a day, but it's not going to take many thousands of years because we see this acceleration now. And so that's another thing. So we have time, but we do not have much time. But mostly we have to start going down the right path as aggressively as we possibly can today, because the longer we wait, the more damage we have to undo. And there may become a time, just as with smoking, that there could be a point of no return. And the point of no return is when the globe gets so warm that huge amounts of carbon dioxide in the tundra and other places begins to emit well beyond what humans emit. And that is a runaway effect. And if we reach that, that is a point of no return.
Another question, Dr. Xu. Which industries do you think will be most affected by the new clean energy standard and the path to net zero?
Well, I think electricity generation will be certainly affected. Transportation are going to be affected. I think I'm hoping, although it's much more politically delicate, that we motivate and do a new agricultural revolution that farmers will gravitate towards because they become more productive, that their lives become better. And so it's things like that that my optimism says we can use technologies and use this relationship between the microbes in the soil and plants at a local level where poor farmers can become much more productive. Their standard of living increases, and they will want to do this. You don't need a law to do something which is better for people. We do need laws that prevent wholesale pollution. You do not want chemical factories dumping things into rivers and oceans and lakes. But these other things can be found if the technology is so good. It's like the cars. You know, cars don't poop. Therefore, they were better than horses. And so we went very quickly. Now I've got to apologize. It's 3:15. I'm supposed to teach a class of undergraduates, special relativity and quantum mechanics. And it's now, I'm 1 minute late for my class.
So, Dr. Xu, thank you very much for all your answers and for sharing your knowledge with us. It's been a pleasure to meet you. Thank you very much.
Okay, thank you all. Okay, goodbye.
Thank you, Mr. Xu, for sharing your knowledge and concepts. We are convinced that your conference will be very helpful for all of us in the future. Sin duda, el amplio conocimiento del tema por parte de nuestro invitado nos arroja mucha luz sobre el desarrollo sostenible y su vinculación con las empresas globales, los que nos permite vislumbrar nuevas oportunidades en el desarrollo de los negocios. Como ya lo dijo Kofi Annan, exsecretario general de la ONU, y lo cual señalamos en nuestra invitación, hay un nuevo entendimiento universal de que las fuerzas del mercado son esenciales para el desarrollo sostenible. Es por eso que buscamos traer estos temas a la mesa de discusión, explorando nuevos horizontes para los proyectos de inversión de nuestros clientes, siempre de la mano del equipo mejor calificado en el mercado, el de Vector y Vector Global. También quiero agradecer a Claudia y Pablo por su colaboración durante la sesión de preguntas y respuestas que nos permitió agilizar la dinámica y volverla muy atractiva para los presentes.